sand is being poured into a conical pile so that the pile always forms a cone whose height is twice the radius. The sand is added at a rate of 5 cubic meters per minute. How fast is the height of the sand pile increasing when the height is 4 meters? The volume of the cone is increasing at a rate of 5 cubic meters per minute, so that means dV over dt equals 5. We need to find the rate of change of the height with respect to time, so that's dH over dt. And we need dH over dt specifically when the height is 4. Since the height of this cone is always 2 times the radius, we can use the height to solve for the length of the radius at the same instant. The radius equals h over 2, so if h is 4, that means r is 2 at that same instant. We'll also use r equals h over 2 in our volume formula. Volume of a cone equals 1/3 area of the base times height. We'll assume the base is a circle, so we have pi r squared for area of the base. Remember that we're trying to solve for dH over dt, and we know that r equals h over 2. We can plug h over 2 in place of r in the volume formula. Then we have volume of the cone as a function of h, where h is the only variable on the right side. Using properties of exponents, h over 2 in parentheses squared is the same as h squared over 2 squared. H squared times h will equal h cubed. Multiplying the constants together, we get pi over 12 times h cubed is equal to the volume. Remember that we're trying to find the rate of change of the height with respect to time. So we'll need to take the derivative with respect to time of the entire volume equation. Which means we'll take the derivative of the left side and derivative of the right side. Notice that we're taking the derivative with respect to t, but there are no t variables in the equation. So we need to use implicit differentiation. For the right side of the equation, this means that we'll take the derivative with respect to h, and then multiply by dH over dt. In a way, dH is cancelled out and we end up with the derivative with respect to time. Derivative with respect to t of v will be dv over dt, but we could also write the step similar to the right side of the equation. So derivative with respect to v of v times dv over dt. So notice that derivative with respect to v of v is equal to 1, just as derivative with respect to x of x is 1. To take the derivative of this expression, we'll use power rule. So we have 3 times pi over 12 times h squared. Remember that to get the derivative with respect to t, of an expression with only h's and no t's in it, we first take derivative with respect to h and multiply by dh over dt. So derivative with respect to h is this expression in yellow. And then we have dh over dt in purple. Three twelfths will simplify to equal 1/4. Now we can plug our values in and then solve for dh over dt. One of the 4's can cancel so that we have 4 pi. Divide both sides by 4 pi. Then we get dh over dt equals 5 over 4 pi, which when we plug into the calculator will get approximately 0.398. Since dv over dt was measured in meters cubed per minute, and the height and radius are both measured in meters, dh over dt will be measured in meters per minute, since height is a length.